All right, so good evening to all the participants and welcome to the third webinar on Plaxis webinar series, the Tuesday series. I'm very sure that the earlier two webinars would have been helpful in understanding the basics of numerical analysis and the application of Plaxis 2D specifically in case of industrial problems. So in the third webinar, what I'm going to do is that I'm just going to extend the discussion about the application of Plaxis 2D for rock mechanics problem. Specifically, I'll be dealing with the rock slope stability analysis. Although today's webinar or today's presentation will specifically talk about rock slope stability, rest assured that whatever you're going to pick up today can be easily extended or mapped for discussions in case of tunnels in rock strata. So to start with, first of all, I would like to highlight that a lot of discussions are made or a lot of queries are generally asked that which is the software which can be used for analysis of geotechnical problems in rocks. Recently, Plaxis has implemented a very powerful constitutive model, that is the jointed rock mass model in Plaxis 2D as well as Plaxis 3D. And I have been extensively using it for my research purpose as well as for some consultancy services. And I found that this application or this specific constitutive model helps to validate and even make critical decisions when it comes to designs and assessing the stability. So today's webinar will be spanning for about 30 to 40 minutes. For the first 20 minutes, I'll just have a general theoretical discussion on various issues. This will be restricted to about 1 to 2 slides. And once I am done with this, once I give you the background about your rock slope behavior or rock mechanics problem, what I will be doing is that I will just demonstrate right at the end the rock slope stability analysis in Plaxis and discuss some of the results. So I will try to make a model using the Plaxis software, so all of you can get a hands-on experience about how to set up the model and run it. But the analysis will take some time. So what I have done is that I've already done the analysis, and hence I will discuss the results of the model which I set up. So today's presentation will start with the discussion on the importance of slope stability. This will be followed by a brief discussion about the differences between soil slopes and rock slopes. That is, first of all, we'll try to understand that what is the failure mechanism which we expect in case of soil slope, and whether the same failure mechanism happens in case of rock slopes or not. And if it does not happen, then why do we need to go for a different constitutive model in order to correctly predict what kind of behavior is going to come? That is where I'll have a brief discussion about the strength of the jointed rock, where we will talk about how the geological discontinuities or the joint sets or the inherent cracks which you generally see in mountainous areas in rocks affects the strength of the rock, and how it is going to eventually have an impact on the entire behavior of the rock slopes. Then I will highlight specifically the jointed rock model, which is included in Plaxis, both in Plaxis 2D and 3D. And the validity of the jointed rock model will be discussed. Remember that since we have a numerical analysis tool available with us, it has a number of features. So we need to be very careful about choosing the correct feature to eventually do any meaningful analysis. So that is where the validity of the jointed rock model will be highlighted. Finally, how the safety analysis is carried out in Plaxis, a brief background about that will be provided. It is similar to the strength reduction factors or the strength reduction methods, or it is known as the 5C reduction method in case of Plaxis. So I will provide a brief background towards that specific method. And finally, the demonstration of the rock slope stability problem in Plaxis will be dealt with. So when I talk about rock slopes, this is a photograph which is very much drives the importance of the entire problem statement. So this specific site which you see on your screen right now is the Tindaria landslide. Specifically, it is in the Darjeeling district of West Bengal, and this site is very famous because it is a UNESCO World Heritage Site. What you see in the figure right now is a national highway, a portion of which has been washed away, and a portion of the track which is being operated by Darjeeling Himalayan Railway for their famous toy train, which is seen hanging. Now, this specific landslide happened in the year 2011 following the Sikkim earthquake, Following the earthquake, there were some cracks in the ground, and then there was heavy or intense rainfall. And following this, eventually 10 days following the earthquake, a portion of national highway and the railway track was washed away. So this is what you see. So it caused a great deal of distress to the people in the area. The This is the road which is the lifeline for the people living in mountainous areas, and protecting infrastructure or connectivity in those areas is very critical. We all understand that how critical it is as a lifeline structure, these structures in mountainous areas. So this is the motivation behind me taking up landslides as an area of active research, and I've been working in this field for over 10 years now. And what you see over here is a very interesting thing. Over here, you can see that the exposed surface comprises of rocks and soil. So it is basically the soil which you see is the weathered rock or rock mass, which has eventually been converted into a soil-like material. But mostly the failure surface, when you visit the site, you will see that it mostly comprises of rocky strata. Similarly, there are other cases of slope instability which is of great importance. The case of, let's say, railway tracks passing through areas adjoining rock cuts. So in the present figure, again, you can see there are two railway tracks. The right track or the track adjacent to the rock cut has been destroyed because of an instability happening over there. Again, we do not intend to have a construction or an intent to have infrastructure in such cases, or we need to be very sure about how the adjoining slopes are going to behave in case critical infrastructure is passing through such conditions. Apart from the civil engineering applications in the field of roadway networks and railway networks, there is additionally one more wide application of slope stabilities, which is in the mining industry. So now we know that the extraction of materials or minerals has led to the excavation at deep depths, and along with the extraction of the minerals, one associated issue is the dumping of the waste material. Generally, we have dump slopes, and these dump slopes may range in height, ranging from anywhere between 50 to 100 meters to even 500 to 600 meters. When we are dumping such material, or when we are going for such type of a configuration as shown in the right hand side of the figure, again we need to be very sure about how those slopes are going to behave, because any failure or any instability which happens in the case of mines, it will not only have an adverse impact on the mining operations, but sometimes it can have adverse impact on the machinery, and in some unfortunate conditions you may even have loss of lives, which is not at all desirable. So this is where the slope stability comes into picture, and right now I have tried to restrict my discussion to stratas or to ground conditions which are mostly rocky in nature. Now, if I talk about the observed failure mechanisms, we all have a basic understanding about how the slope is going to fail in case of the ground comprising of soil. So on the left hand side, you have a figure of a soil slope, and right on the top, let's say you have a foundation or you have infrastructure which is getting constructed. Because of the load application, or because of, let's say, any external loading, because of either man-made activity or, let's say, natural activity such as earthquakes, we may eventually land up with a condition where a portion of the ground is going to fail. That is, a portion of the ground will become unstable and it will move out. So a land will basically slide out from the parent body, and hence the term landslide. What has been seen in case of soil slopes is that mostly the failure surface is curved in nature, and the application of Moore-Coulomb strength criteria seems to be quite appropriate in capturing some of the field observed mechanisms. So for soil slopes, the application of, or the adoption of, or employment of Moore-Coulomb strength criteria seems to be fine. However, the issue comes in case of rock slopes. When I talk about rock slopes, there are inherent joint sets or discontinuities which are present. There may be bedding planes also. And the right hand figure just gives you an idea about one such configuration of the joints. And in this case, what happens is that rather than a failure surface which is curved, you will get distinct failure patterns depending upon the orientation of the joint sets. For this specific case, which has been shown on the right hand side, you basically anticipate a portion of the land to basically move out along these straight lines, these straight inclined lines. So this is known as the planar mechanism. So it has been observed from a number of cases that the failure surface in case of rock slopes is not a curved surface. It is mostly governed by the discontinuities, and you may have different failure patterns depending upon the orientation. And in this scenario, the application of Moore Coulomb strength criteria may not be appropriate, or it may not be very accurate. So this is the reason why you need to go for some other constitutive model or some other modeling technique to eventually predict or to eventually accurately capture the mechanisms which governs the behavior of infrastructure constructed in rocky strata. Just to take this discussion forward, let's say that when I talk about the strength of the jointed rock mass, generally we will be having rock samples which will be cored from rock blocks which are extracted from sites. And when we basically do the testing on these rock cores, what has been found is that depending upon the orientation between the bedding planes or the geological discontinuities and the axis of loading, it has been found that the strength of the material is going to vary. For example, let's say that if I'm applying a load of sigma 1 along a specific vertical direction, and as the orientation of the discontinuity planes beta changes from 0 to 90°, you will find that there will be a drop in the strength of the material at angles ranging between 15 to 60°, where around 45° you will find that the strength is the least. So right on the right hand side, what you see is not the failed sample, but these are the rock cores which I have taken out from the Teendaria site. And what you will be able to observe is that there are inherent discontinuities which are present along these cores. So these are the weakness planes, and mostly when you're going for any sort of a construction in such materials, sliding or failure along these planes are the predominant mechanisms, and that needs to be captured accurately. So this is where the jointed rock model comes into picture. Praxis has an inbuilt constitutive model, a very powerful model, I would say, which is the jointed rock mass model. This model basically is an anisotropic, elastic, perfectly plastic model. So it is elastic, perfectly plastic. This model is suitable for stratified or jointed rock layers wherever we have a stratification plane or a joint plane which is parallel, let's say, or a bedding plane. Over there, this rock model can be used to evaluate or investigate a lot of failure mechanisms, both for, let's say, rock slopes, even it can be used for tunnels also. What it does is that the basic formulation of this model is that it assumes that the intact rock uh, will be mostly having an optional stratification and major joint direction. So right on the right hand side bottom, you can see that you can have major joint directions as well as stratification. And you need a number of parameters which characterizes the behavior in this constitutive model. So intact rock is considered to behave as a transversely anisotropic elastic material. Now this becomes important if you see that it is an elastic material. So whenever we are using the jointed rock model, the intact part is always elastic, and that is where you will need 5 specific parameters to be assigned in such kind of analysis. For intact rock, you will need E1, E2, and your Poisson's ratio in the first and second direction, depending upon the direction where you're going to specify, and your G2. Along the major joint direction, that is the stratification plane which you're going to provide, you will be using the Coulomb's criteria, that is the failure along the joint direction will be assumed to follow the Coulomb's criteria. So you will be having a limiting shear strength which will be there, and using this model you can use a maximum of 3 stratification planes. Now this is important, and for most of the applications in rock mechanics, consideration of 3 sliding planes seems to be quite a good approximation or a good idealization. Now, one of the features is that in each of the planes, suppose you're using 3 planes, you can specify the strength parameters of each of these 3 planes if you have measured it in the field. Or if you're using some correlations or classification, rock mass classification systems, or if you have some results, you can eventually decide what type of input parameters can be fed for each of the 3 stratification planes. So the parameters which are generally required for analysis using this model are as follows. First, you will need the anisotropic elastic behavior properties for intact rock. That is where you'll have E1, E2, nu1, nu2, and G2. Then you can have 3 joint planes, and along the 3 joint planes, again, you will be having the option of specifying the dilatancy, the friction angle, and the cohesion. And finally, you can even provide the limiting tensile strength in the three directions. So we will just look into these aspects when I demonstrate that what is the window where you can choose the jointed rock model, and what is the orientation you can give, and how you specify the parameters. So we'll have a look into these parameters. Remember that the orientation and the properties of the fracture planes or the stratification will play a dominant role in the failure mechanism. So that is something which I will try to demonstrate today. Coming to the validity of this model, if you wish to use this model, you have to be very sure about the site conditions existing. In case you have a site where your rock mass comprises of joint sets which are parallel, or more or less it is parallel, then you can use this. Also, you need to be very sure about the distance which exists between the joints. So the distance between the adjacent joints should be small enough in comparison to the dimension of the structure. So in the specific diagrams, again in this slide, you will see that the spacing between the discontinuities or the stratification planes are very less as compared to the tunnel dimension. Or even in the case of the slope, you can see that the joint spacing is very less in comparison to the dimension. So whenever you have these conditions which are meeting, then you can eventually think about using the jointed rock mass model in case you feel that the dominant mechanisms will be captured using this specific model. And like I said, that maximum 3 joint sets can be taken into consideration. The present figure shows only 1, but you can go for 3 specific stratification planes. Now, if I talk about the safety analysis in Plaxis 2D, it is somewhat similar to what we generally do when we talk about strength reduction method. So whenever I talk about safety, you have a resisting force and a driving force which will be coming on the infrastructure. And you know that if the resisting force, which is quantified in terms of the shear strength of the material, if that is greater than the driving force, then it is known as a safe condition. Whereas if the resisting force is less than the driving force, it is the unsafe condition. So that is where the concept of factor of safety comes into picture. Plaxis 2D eventually gives you the answer in terms of factor of safety. So that is where your MSF will come into picture. That is the quantification of your factor of safety in Plaxis 2D. So whenever you see this specific, whenever you basically do a safety analysis in Plaxis 2D, remember that eventually you're finding out the ratio between the resisting force and the driving force. If the factor of safety is greater than 1, it eventually means that the resisting force is more than the driving force. And in case if the factor of safety is less than 1, it eventually means that the resisting force is less than the driving force. So when I say that the factor of safety is less than 1, it means that the resisting force is less than the driving force. So there will be a force which will drive the instability, and a portion of land is going to come out. So that is how you basically define your FOS less than 1 as an unsafe condition. So Plaxis 2D supports automatic detection of failure surface since it is a finite element package. So it basically you do not need to assume any failure surface, which is the major limitation when you use limit equilibrium softwares. So Plaxis 2D has an automated feature which will detect the failure surface, and it evaluates the safety through the technique which is known as the 5C reduction technique or your shear strength reduction technique. If I talk about the 5C reduction technique, what it eventually means is that suppose you have a slope, and on top of slope you are going to eventually carry out some construction. As a result of construction, you will have a specific stress state in the ground, which can be represented in the form of a Moore circle as shown in this specific figure. Suppose that, let's say, presently the strength of the rock mass is sufficient enough to resist the loads, or it is safe enough to go on with the construction. You will have a line which is shown as the red line overhead. So that is where you will have a specific C and a specific phi or a tan phi. What will happen is that for this specific configuration, Plaxis 2D is going to run a number of analysis iteratively, where it is going to reduce the strength of the or the strength parameters of the rock mass. That is, it will reduce the cohesion and the friction angle of the rock mass by a specific factor F. So once we do that, what will happen is the red line will shift downwards, and eventually we will land up with a condition where the Moore circle will be touching the reduced shear strength line. And it is at that condition that your resisting force and your driving force will become equal. And at that specific point of time, your Plaxis computation will complete, and It will come out from the analysis module and then you can view your output. So if your reduction factor is greater than 1, it eventually means that it is a safe condition, and that is where you can decide that whether your instability or stability conditions are there or not. So this is all about the background of the safety analysis which you carry out in which you can use for carrying out any rock slope stability analysis in Plaxis. So today what we are going to do is that we are going to basically demonstrate to you the features available in Plaxis 2D for carrying out the slope stability analysis using the jointed rock model. So in this specific diagram, what you see is a generic slope. The slope angle is given as 50 degrees, and there are two cases which I have considered. The first condition is a condition where you have your joint orientation at as 30 degrees, and I think there's a mistake. The second joint orientation is 120 degree, not 50 degree. So on the left hand side, what you see over here where my cursor is moving is your 30 degree joint orientation, and this is your 120 degree joint orientation. The height of the slope which has been considered is 25 meter. The density of the material is 20 kilonewton per meter cube. We are assuming that the cohesion along the stratification planes is 100 kilonewton per meter square, and the friction angle of the joint or the stratification plane is 20 degree. So if I want to carry out this specific analysis right now, I'll just make a correction over here if this is shared. So 120 degree is the second case. In case if I want to carry out this analysis, we can basically carry out this analysis using the graphical user interface. So if you have your Plaxis 2D available, what you can do is that you can first of all go to the structure module. Since the rock domain right now is not a rectangular body, but it is a slope, what we will be doing is that in the structure modules, we will be making use of the create soil polygon to make the geometry. So right over here at the top, you have a create soil polygon. When you click on that, you can basically create a sort of a rock slope using this specific feature. So it's very easy to set up a numerical model in Plaxis. One of the ways of setting it up is that even if you know the coordinates of the, let's say the rock slope, you can just use the command line which is given in the bottom, where you just make use of the command polygon and then you just specify the coordinates of the rock slope or any slope to create the geometry. So what we are going to do is that we are just going to set up this model step by step. First, I will demonstrate how you set up the geometry. Then I will go on to define the rock mass. There I will let you know that how the jointed rock mass model, what are the inputs which are required, how we can incorporate 2 joint sets or 3 joint sets. And then I will move on to the stage construction where I'll let you know how to set up a factor of safety analysis or a safety analysis. So I'll try to do that right now. So if I just create on the create soil polygon, right at the bottom there is a command which says that underscore polygon, and I already have the coordinates of my slopes available with me. So I'm just going to copy that and paste it over here. And once I do that, you will see that a rock slope has been created. So if you see that this is specifically the coordinates which I have worked out for the problem which I have highlighted. So this is where you are going to set up your geometry of the model. Once you have done it, right at the bottom you have a materials tab, and if you click on that, the materials sets tab will open up or it will pop up. Over there you can basically click on the new button and you will be given the option of specifying the properties of the ground which you wish to incorporate in the numerical simulation. So in the material set, the identification, I'm going to keep it as the rock mass. And this is where your material model comes into picture. So if you just click on this, you can see that a lot of constitutive models are available in Plaxis. And that is why I feel that this is one of the most robust softwares because it has wide applications in a number of domains or a number of fields. And that is where you can even go for the jointed rock model in our case. So when I click on the jointed rock model, what can happen is that over here you have your general parameters and other tabs. I'm going to restrict my discussion only to the general and the parameters tab. I'm going to specify the density of the material as 20 kilonewton per meter cube as per my problem statement. And now the most important part. When you come to the parameters part, what you see on the right hand side is the probable stratification planes which you can incorporate in Flaxis. So if you look over here closely, you have a strength tab, and over there you have an option of number of planes. If I basically select two number of planes, there will be additional dialog boxes which will be opened up or which will pop up. And now you can see on the right hand side, there is two planes, plane 1 and plane 2. Alternatively, I can even go for three planes. So depending upon the site information or your field survey, or depending upon the amount of data which you have, you can incorporate three joint planes or three stratification planes in Flaxis. Now, if you look into this, I'll just make it a bit simpler. If I talk about one specific plane, the orientation which you see right now is horizontal, and that is the orientation which is corresponding to 0 degrees. So if you look over here, that is plane 1. Right at the bottom, you have the option of specifying the inclination. For example, this is 0 right now. If I give 30, you will see that on the right hand side, it gives you the visual a visual representation of the joints which will be incorporated in your joint model or in your rock slope right now. In case if I give 45, what will happen is that the joint direction is going to change. Let's say that I give it as 125. Again, the joint direction is changing. If I had, let's say, two planes, I could have given the second plane as 30. So that is where you will see a green line and a red line. So the green line corresponds to plane 2, that is 30-degree orientation, whereas the plane 1 corresponds to plane 1, which corresponds to 125 degrees. So like this, you can specify the geometrical orientation of your joint sets on the cross section of the slope which you have evaluated. So this is how we can incorporate multiple joint sets in Flaxis. Just to keep things simple and to keep our discussions in line with the problem statement I have given, I'm just going to input the parameters. That is, let's say E is 20,000 kilonewton per meter square. Resistance ratio, I'll keep it as 0.3. I will not go for, let's say, I will not go for an anisotropic condition. So I'm keeping the E2 and mu2 to be the same. If you want, you can eventually change it if you have enough lab data. And 7962. This works for me. And the cohesion value, I will put it as the cohesion of the stratification plane as 100 kilonewton per meter square, and the friction angle as 30 degree, and the joint set angle right now as 30 degree. Sorry, the friction angle will be 20 degree as per my problem. So when I have this, I'm just going to click on OK. So your material sets tab will have a material named as rock mass. If you just go on edit, you will be able to see the parameters which you have specified. So this seems to be correct, whatever I have done and whatever I wish to incorporate right now. I'm just going to pick this rock mass and I'm going to drop it onto the slope. So once you do that, what you see is that the color of the geometry changes. This means that your material properties are now assigned to your geometry. That is where you could have used a command also, or that is where whatever things you're using with the help of the graphical user interface is captured in the form of a command line. So if you become conversant with this, it becomes very easy to work with Flaxis 2D. Now, once we are done with this, I'll just go to the meshing. Remember that meshing will play a very critical role in the calculations. So right now, I'm just going for the meshing in terms of a very fine mesh. So the sensitivity or the convergence study needs to be carried out. So that is something which is very necessary for all the analysis. But right now I'm just demonstrating it with a very fine mesh. So let us see that once we mesh it, let's say that once I'm using a very fine mesh, it says right at the bottom that we have generated 933 elements and there are 7,600 plus nodes in this model. So if we wish to see the, let's say the mesh which has been generated, I'll have to open up the output module. So this is where you can see the model which has been generated right now with the mesh. So seems fine at this stage. Now once I'm done with this, I'll move on to the stage construction and I'll just toggle, or I'll just activate the rock mass right now. So you have an initial phase, and since this is not a surface which is horizontal, hence we should not be using the Kinot analysis, and we will be using the gravity loading. I'm very sure that earlier webinars might have spoken about this. So that is where your initial analysis, the loading type has to be, the calculation type has to be in terms of your gravity loading. Once you're done with this, I'm going to create an additional phase. That is the first phase, and I'll keep it as the plastic phase. Let's say that let me do a calculation with the plastic phase, and following that, this is where your safety analysis will be carried out. So over here, what you're going to do is that you're just going to click on this calculation type, and you're going to click on safety. When you click on safety, this is where your strength reductions or your 5C reduction method comes into picture. If you do not choose this safety, then your 5C reduction will not be carried out. So remember that in order to carry out a stability analysis in terms of factor of safeties or shear reduction, you need to basically go for the safety type of calculation. Once you are done with this, as a good practice, it is always advisable to choose specific points in the model to see that how those points are eventually going to move out, or how those basically behave when you are going to reduce the strength of the material with regard to some factors. So you can just click on this triangle, which will help you to select specific points or nodes. So what I'm going to do is that I'm just going to select specific nodes right now. And you will land up with something, a figure in your output module, which will show you slope configuration. So we know that the vulnerable section will be somewhere at the bottom. So I'll just click on that. I will click one more point over here right now, and the crest of the slope, and I'll just update. So once we are done with this, we can eventually go for the analysis. And if I click on the analysis, that is the calculate, your analysis will start. So this will take some time. So what I'm going to do is that I'm just going to stop this analysis at this stage. I have already done this analysis for 30° and 120°. So I will show you the results, and I will let you know how it compares with the experimental findings. But at this stage, I would also like to highlight some of the advantages or some of the features which I like about Flaxus. If you just go to the model conditions, if you go to the deformations, the boundary conditions are already defined. So remember that whenever you do any analysis, you just have a look at the boundary conditions you're using. For example, right now it says that your x minimum and x maximum are normally fixed. That is, the model is fixed at the vertical boundaries on both the ends in the horizontal direction, whereas your y minimum, that is the base of your model, is fully fixed. That is, the movement is restricted in all the directions. Now the y max, as you expect, in case of slopes, it needs to be left free. So that is where your y maximum is completely free. At this stage, I would also like to tell you that suppose you want to do an analysis in which you intend to see what will be the effect of the slope following the application of the load. What you will need to do is that you will just need to go back to your structures module, and right above the create soil polygon, you will have a create line. So you can just create lines depending upon what is the length along which you wish to apply the loads, and then you can just apply the line loads over there. And if you just click on the line loads, you can have an idea, or you can basically impose the loads which you anticipate from your infrastructure. And then you can go for your stage construction and do all sorts of analysis depending upon the sequence of construction or the sequence in which you wish to capture the behavior of the slope. So that is where I have already done the analysis for both 30° and 120°. So I will present the results for both 30° and 120° and try to highlight the validity of the results. So if you see the case of 30°, what you will find is that you have the initiation of the failure happening at the toe of the slope, and right at the end of the analysis, what I see is that we have a distinct plane, an inclined plane along which your yielding is going to happen and along which your displacements are going to happen. So this is the failure mechanisms which I anticipate for planar rock slopes, where you have your joint planes daylighting into the slope face. And just to give you an idea about how the failure mechanism is eventually being captured, you can see that from your failure analysis output from Plaxis, you will find that there is a failure predominantly due to the shearing along the joints. So right now the factor of safety came out to be somewhere around 2.18, which holds true mostly with the hand calculation for planar failures. I have tried it, so the error is not very high. We can improve it further by basically working on the meshing. Now, what is interesting to note is that for the same parameters, strength parameters of the joint sets, I had just changed the orientation of the joint sets. Now you see that the failure mechanisms have changed. Now you will see that you will have an inclined straight line and you will have one more line cutting it across in a perpendicular direction. So this is the displacement plot on the left hand side, and on the right hand side you have these strain plots. So what you can see is that there are two distinct failure planes which are there. Now why does this happen? This basically happens because of the orientation of the joint. If you see that 120-degree, the orientation will be somewhere like this, something like this. So as anticipated, the failure mechanisms have changed, although the strength parameters have remained the same. On the left hand side, what you see for 120-degree is the shear failure plane. And you will see that now the shear failure plane does not eventually extend up to the top of the slope. But if I try to superimpose the tension points or the failures which has happened because of the tension cracking, what you will find is that there is a distinct plane which is touching this shear failure plane and joining with the top of the slope surface. So if I try to validate this with some of the lab results which has been reported, you will find that even in case of lab conditions, you will find that whenever the orientation is in a direction as shown for the case of 120-degree, the entire failure is initiated as a result of tensile cracking developing at the top, which eventually is going to drive the shearing along one specific direction. So that is something which is captured using the Plaxis jointed rock mass model. So this is how you can use your jointed rock mass model to eventually evaluate the mechanisms of failures in rock slopes. This can also be extended to your tunnels in rock mass. I have been using it and I found that very good results with what has been reported in the literature and in all the research articles. For some consultancy purposes also, what I have seen is that Plaxis 2D gives results which are very accurate and which corresponds well with the field data which has been instrumented. So in this case, for the toppling case, what you see is that for the same strength parameters, the factor of safety now basically reduces and it is around 1.9. So that is where your jointed rock mass model is a very advanced model, I would say, and it is able to capture most of the failure mechanisms in case of rocky strata. And I feel that this can be utilized for a number of studies where